Hey people, let's start learning for earning.
Additive rapid prototyping processes like SLA and FDM are excellent for checking form and fit, but the moment you subject those layered plastics to real-world mechanical stress, you hit a hard structural limit. They reach their crush point and fail. To test actual structural components, parts that will bear physical loads inside working machines, engineers rely on subtractive rapid prototyping, or SRP. Instead of building up fragile plastics layer by layer, SRP cuts waste away from solid blocks of industrial-grade material. If a final production part needs the thermal resistance of steel, the low weight of aluminum, or the impact strength of polycarbonate, the prototype can be machined from those exact same materials. To shape those materials, we use the broader ecosystem of computer numerical control, or CNC machining. The entire discipline splits into two primary branches, depending on the geometry of the material removal process. In CNC milling, the workpiece remains stationary, while a rotating cutting tool moves across it to carve out shapes. In CNC turning, the opposite happens. The material itself spins at high speed, while a stationary blade pushes into it to create cylindrical profiles. Machining these materials requires more time and operator skill than hitting print on a desktop 3D printer, but it forces a designer to deal with tool clearances and the raw physics of aerospace and medical manufacturing from day one. An engineer who designs for subtractive manufacturing learns early on whether a part is too expensive or physically impossible to make. Once you know what you are machining, you have to hold the raw material in place against the massive torque of the cutting tool. And whether you are making a single prototype or a million units, the primary strategic difference is your work holding. If you only need one or two parts, the goal is minimal time investment. Machinists will rely on cheap, off-the-shelf solutions, standard vices, toe clamps, screws, or even double-sided tape. The operator might spend 10 minutes manually clamping the part, but for a single unit, that labor cost is negligible. Mass production inverts that logic. When outputting tens of thousands of units, manual clamping is too slow. Manufacturers invest heavily up front to design and build highly elaborate custom hydraulic or mechanical fixtures. This chart illustrates the economic strategy. A custom fixture requires a steep capital cost on day one, but as production volume scales past 1,000 units, that fixed cost is amortized, spread out over so many parts that the cost per unit approaches zero. A custom fixture might save just 30 seconds of loading time per cycle. Over 10,000 cycles, that prevents over 80 hours of idle machine time. At the crossover point, the massive upfront cost of the custom tool becomes mathematically cheaper than the slow, manual process of the prototype. A design is only viable if the engineer has mapped their fixturing strategy directly to their target production volume. Getting to that physical production stage requires passing the design through the digital thread. This is a strict 9-step information pipeline that translates digital intent into mechanical energy. Step 1 is computer-aided design, or CAD. At this stage, the model exists purely as geometry. It is a weightless, abstract representation of dimensions and design intent. Steps 2 through 6 transition the model into computer-aided manufacturing, or CAM. This software acts as the bridge. It forces the abstract CAD shape to comply with the physical strategy of actually cutting metal. Step 2 establishes the coordinate system and exact dimensions of the unmachined stock. Next, the programmer configures the tool library with exact cutter dimensions. Finally, the CAM software calculates the precise linear and helical routes those tools must take through 3D space. These paths are divided into distinct operational phases. The sequence usually begins with facing to create a perfectly flat starting datum, followed by roughing, an aggressive operation designed to remove the bulk of the waste material as quickly as the tool can handle. Once the bulk is cleared, the process switches to finishing. The machine takes shallow, precise passes over the remaining material to hit the final dimensional tolerances and achieve a smooth surface quality. This image shows the continuous, curved blades of a jet engine turbine. Geometries this complex require CAM platforms capable of calculating simultaneous multi-axis finishing paths. CAM software is the gatekeeper. It forces digital idealism to submit to the physical reality of tool shank diameters, chip clearing clearances, and the stubborn hardness of the raw material. With the paths calculated, step 6 is tool path verification. A machinist must digitally simulate the entire sequence to spot physical collisions before they happen, preventing a multi-$1,000 crash between a spinning tool, a steel clamp, and the machine table. Once the simulation is clean, step 7 is post-processing. This is the moment the visual toolpaths are mathematically translated into the specific numerical language understood by the machine. This dense block of text is G-code. It's a sequence of rigid coordinates dictating spindle speed, coolant, and axis movement. Every line translates to a precise micro-movement of the cutting tool, carving the stock. The code is the literal physical trajectory. In step 8, this raw text file is transferred directly into the memory of the CNC machine on the shop floor. The machine control unit reads G-code and converts it into electrical velocity commands for the drive motors. Crucially, industrial CNC uses a closed-loop system. An encoder reads the motor's exact physical location, sending a position feedback signal back to the MCU thousands of times a second. This constant high-speed feedback loop is the foundation of modern precision. It ensures that heavy, industrial hardware perfectly and repeatedly traces the exact coordinates of a weightless digital file. The modern manufacturing pipeline is ultimately an unbroken flow of structured information. It starts with an abstract CAD model, locks into strict real-world dimensions during job setup, and funnels into a specific subtractive process. The programmer arms the machine with precise physical cutting tools, then calculates the driving geometry required to carve out the part. They simulate the physics to avoid catastrophic collisions, and post-process those visuals into raw alphanumeric G-code. That code is transferred to the machine control unit, commanding heavy access motors under constant, closed-loop scrutiny. And the viability of this entire flow depends on volume, deploying agile, off-the-shelf work holding for prototypes, and amortizing the cost of custom-machined fixtures for mass production. Engineers today do not simply sketch shapes, they manage this digital thread. Their core responsibility is ensuring that the purity of their design intent can actually survive the violent physics of the machine shop. Mastering subtractive rapid prototyping and the CAD to CAM pipeline pulls an idea off the screen, cuts away waste, and leaves a functional, real-world product.
Thanks for watching, and please like, share, and subscribe for such more content and appreciation. Make sure to comment your questions and